Welcome to The Explainer. We all learned that a rainbow is just sunlight hitting raindrops, acting like little prisms. Simple, right? Well, today we're going to dig way deeper and uncover the truly surprising physics behind it.
All right, let's just jump right in with a question that seems, well, kind of obvious. Why is a rainbow an arc? Why a curve? And come to think of it, why do you only ever see one when the sun is behind your back? Turns out the answers are way more complex and honestly cooler than you'd expect.
Okay, here's another one for you. Have you ever noticed that the sky above a rainbow is actually darker than the sky below it? Really look next time. Why is that? Well, it has a name. It's called Alexander's dark band, and it's a massive clue that helps us figure out what's really going on. And this one might be the weirdest of all. How on earth can a simple pair of polarized sunglasses make a gigantic rainbow just vanish? Like, gone. What's up with that? So to get to the bottom of all these riddles, we've got to shrink our perspective. We need to go from looking at the whole sky down to what's happening inside one single tiny drop of water. Okay, so let's do it. We're zooming way in. All we care about right now is one little raindrop and one single ray of sunlight hitting it. Now, that simple prism story we all learned, it's not wrong, but oh boy, the full story is so much more interesting. So, the journey of light that actually makes a rainbow happen has these three super important steps. First, the light ray enters the drop and bends. That's called refraction. Then it bounces off the inner back surface of the drop, a reflection. And finally, it leaves the drop, bending one more time as it goes from water back out into the air. Now, this next idea is probably the single most important concept for understanding a rainbow. Listen to this. The light doesn't just scatter randomly in all directions. No, it gets concentrated. Because the raindrop is curved, it focuses the light rays into something called a caustic. And you've totally seen this before. It's the exact same physics that creates those bright, wavy, shimmering light patterns at the bottom of a swimming pool. That's a caustic. Okay, so here's the magic number. For red light, it turns out that all these different light rays hitting the drop get bunched up and shot back out at a maximum angle of 42 degrees from the direction they came in. This is what creates that super bright caustic. It's wild. Light can hit the drop all over the place, but it all gets funneled out right at that specific angle. And this is how we get the colors. So light is an electromagnetic wave, right? Well, higher frequency light, think blue and violet, interacts a little more strongly with the charges in the water molecules. This actually causes it to slow down more inside the water, which means it bends more sharply than the lower frequency red light. It's a tiny difference, but it's everything. And here's the result of that. Each color gets its own special magic angle. Red light, which bends the least, comes out at that wide 42-degree angle. But blue light, which bends more, comes out at a tighter angle, around 40 degrees. That little 2-degree gap between them, well, that's the secret to the entire rainbow. Okay, so that's the story for one single drop. Now it's time to zoom back out. How in the world do billions of these tiny, light-bending, color-separating drops work together to create that one magnificent arch we see stretched across the sky? This part is so important. Every single raindrop isn't just shooting out a single ray of light towards you. Nope. Each one is projecting a full 360-degree cone of colored light. And for that cone, red light makes up the outer edge at 42 degrees, and blue light makes up the inner edge at 40 degrees. Every drop is doing this.
And this leads to a pretty mind-bending realization. A rainbow isn't a thing. It's not a physical object out there in the sky. It's a personal optical illusion. For you to see red, there has to be a raindrop positioned at that perfect 42-degree angle between the sun and your eyeball, which means the rainbow you see is unique to you. The person standing next to you, they're seeing a completely different rainbow made from a different set of raindrops. In fact, your own two eyes see slightly different rainbows. Wild, right?
All right, now that we've got this whole magic angle and caustic thing down, we can go back and finally solve those mysteries we started with. This is the fun part.
So what's going on with the double rainbow?
Well, it's pretty simple, actually. It's just light that reflects twice inside the raindrop instead of once. That second bounce changes the math. It sends the light out at a much wider angle, about 50 degrees, which is why the second rainbow is always higher up. And it flips the colors. So you get red on the bottom. It's all just geometry.
And remember that dark sky between the two rainbows, Alexander's band? Well, now it makes perfect sense. It's literally a no-light zone. Light that reflects once can only get to you from angles up to 42 degrees. Light that reflects twice can only get to you from angles of 50 degrees or more. That gap in between, from 42 to 50 degrees, nothing. No light from either process can reach your eye from that part of the sky, so it looks dark.
Okay, and the sunglasses trick. This is so clever. When light reflects off a surface, like the back of that raindrop, it becomes polarized. That just means its electric field starts vibrating in one primary direction. For a rainbow, that direction is lined up with the arc. Well, guess what polarized sunglasses are designed to do? They're designed to block exactly that kind of reflected, polarized light. That's how they cut glare. And since the rainbow is made of that exact kind of light, poof, it disappears. But wait, the story isn't over. There's this amazing final chapter to the physics of rainbows. A much smaller, related phenomenon, something called a glory, that you might see from an airplane, actually led directly to an invention that won a Nobel Prize and completely changed the course of physics. So get this. Back in 1894, a scientist named C.T.R. Wilson is up on a mountain in Scotland, and he sees his own shadow cast on the mist below. And around his shadow's head are these beautiful colored rings, a glory. He was so captivated that he became obsessed with trying to make them himself back in his lab.
And just look at this journey. His simple obsession with making a little misty rainbows led him to invent something called the cloud chamber. But then he made an accidental discovery that was way bigger. His little chamber could actually make the invisible tracks of subatomic particles visible. For the first time, we could see the paths of electrons and other particles. It was a massive breakthrough that completely changed physics and, yeah, won him a Nobel Prize, all from trying to understand some colored rings.
So, after all of that physics, here's the ultimate takeaway. A rainbow isn't an object. It's not a thing that's out there in the sky. You can't fly to it, you can't find the end of it.
Instead, what a rainbow really is an experience. It's a personal optical illusion created just for you by the perfect alignment of the sun, billions of tiny water droplets, and your eyes. It's one of the most beautiful examples of incredibly complex and elegant physics hiding in plain sight.
You know, it's a great reminder that just looking at something isn't the same as really seeing it and understanding it. And it kind of makes you wonder, doesn't it? What other everyday things that we take for granted are hiding this kind of beautiful, elegant physics, just waiting for us to ask the right questions?